So we have just seen that the one-to-one mixture of two enantiomers is called a racemate and has zero optical rotation. Now what happens if we have a mixture of two enantiomers which is not exactly one-to-one? Then such a mixture will have a certain optical rotation depending on which enantiomer it has, and that rotation will vary with the difference in the composition between different kinds of mixtures. And to quantify that, we use concepts of enantiomeric excess, which is very closely related to another quantifying concept, and that's of optical purity. So if you think of the composition of our mixture of enantiomers as going from plus enantiomer to racemate, and then over to minus enantiomer, in this case we'll have a pure plus enantiomer which will have a certain alpha value. Here we will have a mixture of one-to-one plus and minus enantiomers, and our alpha value will be 0. Whereas here we will also have a pure minus enantiomer, but this rotation will be minus alpha. Okay? And so to answer the question and to quantify our position along this continuum, we use the concept of optical purity, which is also abbreviated as OP, and which simply compares two values, one which is specific rotation for a pure enantiomer, and let's say this plus 13.5, and then the measured value for our enantiomer. So this is alpha measured for our specific mixture of two enantiomers. And say this value is lower, plus 9.2. Okay? Now to calculate optical purity, we will simply take these two values, alpha measured over alpha pure, and then multiply the result by 100%, simply to express it in percent. And so in this case we'll have plus 9.2 or plus 13.5 times 100%, and we'll end up with a 72.0% optically pure enantiomer that we studied. A more common way to do this uses the concept of enantiomeric excess. And even though it's called completely differently, it's actually pretty much the same thing. Which basically, enantiomeric excess, or E, is defined as the excess of one enantiomer over the other. So it's excess of one enantiomer divided by the entire mixture, the composition of entire mixture, and then multiply by 100%. Now what this means is that we'll take the absolute difference in the amount of plus and minus enantiomer, okay, and divide it with the sum of their amount. And since both the top and the bottom of this fraction are in the same units, it doesn't matter what those units are, so we can use percentages or grams or moles of two enantiomers, they always cancel. And so we multiply this by 100%. Okay? And in case we have, say, a 60-40 mixture, so 60% of plus enantiomers over 40% of minus enantiomer, our EE will be 60 minus 40 over 60 plus 40, and times 100%, so this will be 20 over 100 times 100%, which means that we will have overall 20% enantiomeric excess of our plus enantiomer. Now, since enantiomeric excess equals optical purity, we can also calculate the observed rotation. So if, say, the alpha of pure enantiomer is 13.5%, plus 13.5%, then we can get our alpha measured of this specific mixture by multiplying this alpha of pure enantiomer with the enantiomeric excess, and this will be 20%. And then we will get the value which is, yes, 2.7 degrees. Yeah. Both of these concepts of enantiomeric success and optical purity are useful for quantifying the outcomes of reactions that produce chiral products. And in our last topic, I told you that chirality cannot come from nothing. But if we say have an achiral reactant, we can subject this to chiral catalyst, which will now be the source of chirality and will overall give us the chiral product. But the efficiency with which the chirality of the catalyst is transmitted to the achiral starting material will vary. And the good way to quantify that efficiency is by measuring enantiomeric excesses of chiral products that are obtained in this reaction.